folks, welcome back. This is Armand Pantalone, the Chief Technology Officer for Giga-tronics, and we're going to be having another installment of our TEmS Talks. Thread emulation system being the TEmS, and some very specific features of this particular product article. The adaptive real-time closed-loop emulator. There's both an adaptive radar emulator and a cognitive electronic warfare system emulator. And we're going to be showing you a very specific feature set that both of those entities who are foes in the electromagnetic spectrum dominance battle can leverage. And we'll show you some of that feature set today. So what we're going to show you today, the specific feature is pulse descriptor word extraction from received pulse parameters, or RPP-PDW extraction. And what we use to generate that is an RF SoC, an RF system on a chip card in one of our computers. And it's going to be taking in RF and it's going to be sensing it. It's going to be doing digital signal processing, and it's going to be spitting out in real time all of the received pulse parameters that it sees, and it's going to be putting them into what are typically known as pulse descriptor words. So pulse width, PRI, center frequency, etc. And we'll show you how some of that works today. So now that you've seen what the 8-channel RF system on a chip card looks like, including its 8 channels of digital to analog conversion and its 8 channels of analog to digital conversion, we're going to show you that we're going to be using one of the DAC outputs, DAC channel 4, to feed a waveform into A to D channel 1, and we're going to be using that FPGA and all the ARM processors on board to analyze the pulses and give you the pulse parameters in real time. And we do that through a GUI that allows us to show the results of all the pulses processed in near real time with 3 displays. Time domain display, which is just voltage or amplitude versus time. A frequency display, which is frequency versus amplitude. And then a rolling histogram or a spectrogram of frequency versus amplitude in color, and also a time history of that. So we're going to start really simple. We're just going to do a very simple pulse trade of just 1 pulse per second and a set pulse width and PRI and center frequency. So the top of the GUI right here just allows us to create the RF out of DAC channel 4 with all of its pulse parameters, and then we're going to analyze that with the rest of the GUI. So for right now, we're putting out 1 pulse of 10 microsecond pulse width and a 100 microsecond PRI, and it has a dwell of 1 second, or 1,000 milliseconds. And if you look at the screen, what you'll see is the event processor, which sees anytime it sees energy, it's going to create a brand new waveform file and analyze that and spit out the data. So what you're seeing right now is every 1 second it sees a pulse. It's got the correct PRI, and it's got the correct pulse width and the center frequency of 100 megahertz. You can also see the PDWs logged is about 1 per second, just like it should be. So this is just the introduction and starting slow. Okay, so for right now, let's just focus on the frequency analysis, and we're going to leave the pulse width, the PRI, and the rep rate all the same, but we're going to change the center frequency. And you should see on the spectrum display this peak, which is on max hold right now. We can clear that. It's telling us this pulse right now is coming in at 100 megahertz. But we're going to change that in 100 megahertz increments. On the pulse generator, and we should see that reflected in the frequency display. We're going to go up to 800. Now we're going to go up to 1200. Oops. And we're going to push the limits of the D to A, sorry, the A to D. So let's go back to 1250 this time. Whoops. All right. So if you look at the center frequency of the first event trigger, 1 every second, It's got the correct center frequency at 1250 megahertz and the correct rip rate. So now what we're going to do, let's clear this frequency display. We're going to go back to, say, 400 megahertz. You should see the histogram come to 400 megahertz. And we're going to increase the number of pulses. By changing the rep rate. As you can see, the PDW's logged has increased by a factor of 10 per second. And you'll see that reflected in the event log trigger as well. And we can go down even again. And you can see it a much higher rep rate. And we're going to change the frequency one more time to 600. We can show you the time scale. And the next thing we're going to do too is increase the number of pulses to 10. Sorry, let's make it 5. And change the waterfall speed. Okay, we'll show you a few more features in just another second. Okay, so what we're going to do now is give it a little bit more challenging signal than just the fixed pulse width, PRI, and center frequency that we had from the DAC on the RF SoC card itself. So we're going to this other machine, a much more complicated RF playback and generation system for signal generation. You might have seen this in some of our other TEmS Talks videos. So what we're going to do now is we're going to play a 250 megahertz chirp with a fixed pulse width of 25 microseconds and a PRI of 100 microseconds. But what we're going to do is we're also going to change the center frequency of that chirp from 300 megahertz up to 600 megahertz. And I'll show you how that looks on this scope before we put it into the RF SoC card and do the real-time pulse parameter extraction. So without further ado, let me start with a center frequency of 300 megahertz. That's what it's going to look like. You can see the 25 microsecond PRI, sorry, the 25 microsecond pulse width and 100 microsecond PRI, and the 250 megahertz linear frequency modulation excursion or FM chirp. So let me stop that, and I'm just going to show you how we can change the frequency to 500, center frequency of 500 megahertz, and just start again. And we're going to stop that again and go all the way up to, let's say, 600. And we're going to put those 3 different center frequencies through the received pulse parameter extraction. Okay, so we're just going to cycle through same pulse width, same PRI, 3 different center frequencies. We've already piped it over to the RF SoC card for the RPP-PDW extraction, and we'll show you on the real-time display of the PDW extraction with all the event processors and the displays in both time and frequency domain. So without further ado, let me start the first one, and it's going to be centered. The first one is at 300 megahertz. In our spectral display, you'll see the 300 megahertz center frequency with the 250 megahertz LFM or frequency excursion for the chirp, and then also the correct pulse width and the PRI. And let me stop that and go to 500 megahertz center frequency. Move that guy over to 500 megahertz. You'll see the correct 250 megahertz excursion around 500 megahertz. And we'll do that again for, let's say, 700 megahertz. Okay, stop. Okay, so what we're going to do now is we're going to go to the RFPG, the RF playback and generation system, and we'll put in that complicated pulse, a more complicated pulse. Fixed pulse width PRI, 25 microsecond pulse width, 100 microsecond PRI, but it has a 250 megahertz linear FM or chirp on it. We're going to incrementally change the center frequency from 300 megahertz to 500 megahertz and then to 800 megahertz with it piped into the RPP-PDW extraction, and we'll show you that in real time. So to get started, I'll start the first one off, and then we're going to have my my able-bodied lab assistant, Igor, take over and start off the pulse train. So just to start the display, we're going to start the peak, we're going to clear it, and we're going to enable the output or the input to the RPP-PDW extraction. So there you go. You have centered at 300 megahertz. You have a 250 megahertz excursion with the correct pulse width and PRI. We're going to stop that one right now. We're going to increase the frequency, center frequency to 500 meg. There's a center frequency of 500 meg. Again, with the correct pulse width, PRI, and start and stop frequency. And we're going to stop that. Now I'm going to push it up to 800 megahertz center frequency. There. And if you look at the rate at which the PDWs are being logged and generated, and just to show you too, I'm going to remove the signal, and you should see the amplitude, which is green in the mid color scale, should incrementally come down as I slowly disconnect the cable and drop the amplitude of the signal down. And we're gone. I can't really fine-tune it that much. But that's what it would look like. Okay, and we're off. Okay, so in conclusion, now that we've shown you all these pretty colors and all these displays in real time, and the fact that we're writing receive pulse parameter, pulse descriptor words out in real time is really important. But what's the real utility of that? Well, whether you want to use our open open architecture hardware and open architecture software and firmware as a basis for your test systems, or have it just delivered for you. The important thing is whether you want to put a real-time closed-loop adaptive radar emulator in the loop or a real-time closed-loop electronic warfare system in the loop, we have the fundamentals for doing that. None of those systems can do anything without the inline digital signal processing done in real time and the ability to figure out what it's being illuminated, whether it's radar returns for a radar, or whether it's jammer input, like multiple range false targets, or whether it's to an EW system, say like a radar warning receiver, whether it's being searched, tracked, actively engaged, or possibly even in the terminal mode of an engagement with a high PRF waveform. So the ability to do this in real time on the hardware we've shown you, to build a test system around that, to have a real-time closed loop entity inside your hardware and the loop testing is really important. And that's what we're providing today, the open architecture hardware and software to allow that to happen. So thanks again for coming and watching our product demonstration. And as always, both a word of caution and warning, we are what you call professionals, so please don't try this at home.